Hello and welcome to the first video of the Thanksgiving week series for linear algebra. In this video we will be talking about ways to determine whether an infinite series converges, meaning it approaches a number, or it diverges, meaning either it goes to positive or negative infinity, or it just never goes towards a number and goes back and forth. To start this out, I want you to think about each of these series and try to identify which ones appear to converge, which ones appear to diverge, and then see if you can find patterns in those. So, again, I would suggest you pause the video for a second and try to identify. I'll give you a hint. Two of these converge, two of these diverge. Okay? So if you look at these, the first one, and for those of you that were in class on Thursday, this first one, yeah, it converges. The sum from n equals 1 to infinity of 1 over n to the third. You could use the function f of x is equal to 1 over x cubed and integrate that from 1 to infinity. That integral exists, and so, yeah, that first one does indeed converge. Also, the third one, the sum from 1 to infinity of 1/2 to the n, that's a geometric series where the base has an absolute value of less than 1. So those two converge. The last one, 5 over 4 to the n, that's also a geometric series. However, the base has an absolute value of greater than 1, so that diverges. That then leaves this series right here. A key thing about this series is that as n gets large, the inside here will approach 1/5. So now think of it. If we're adding 1/5 repeatedly, that would be like getting 20 cents a day for eternity. Would there ever be a limit to how much money you would get if you got 20 cents a day and it went on forever? It would be limitless. The only way for an infinite series to converge is if eventually you are adding nothing to it. Because otherwise, if you think about it, if you were to get a small amount of money every day for an eternity, you'd never stop getting money. So in order for an infinite series to converge, the inside has to have a limit of 0. If the inside does not have a limit of 0, it automatically diverges. And that is the divergence test for series. So, and again, I would encourage you to pause this to read this over, because I am going to go somewhat quickly so that you can go through this video at your own pace. Going through this, we discussed on the last slide, is that in order for a series to be convergent, the limit of the inside has to be 0. By the way, that does not guarantee convergence. So just to be clear, just because the limit of the inside is 0, that doesn't guarantee convergence. However, if that is not true, then we know the series diverges, and that is the divergence test. If the limit of the inside is not 0, the series must be divergent. So one way to eliminate series that we know are not convergent is just to take the infinite limit of the inside, and if it is not 0, we can write off the series as divergent. So when we look at these three series, we can go ahead and we'll start out with the first one, and again, we are weeding out series that are divergent. So to see if we can weed out the first series, the sum from n equals 1 to infinity of n squared over 9n squared plus 8, we'll take the limit and see if it's not 0. Because if the limit is not 0, we don't need to bother with other divergence tests. Taking this limit, if you might recall from from this past week, to take this limit, one way of doing it is to divide by the highest power of the variable. So we're going to divide the top and bottom by n squared and simplify. Dividing by the highest power of n gives us 9 over 1 plus 8 over n squared. We can then plug in infinity for n, and we know that 8 divided by infinity is 0, which means this limit results in 9. Correction to that previous statement. If we divide by the highest power of n, so we divide by n squared, the top becomes 1, the bottom becomes 9 plus 8 over n squared. Then, from this corrected version, we can plug in infinity for n, and 8 over infinity is 0, which gives a limit of 1 over 9. Because this limit is not 0, this series diverges. We next move on to the sum from n equals 1 to infinity of 5n over e to the n. And again, we can use this test to see if we might be able to eliminate convergence. Again, we cannot confirm convergence, we can only confirm divergence from this test. So again, to perform this, we will take the infinite limit of the inside. In this case, the limit is easiest to do by L'Hopital's rule. So we can take the derivative of the top, which is 5, and the derivative of the bottom, which is e to the n, and take the limit of that result. If we plug in infinity here, we end up with 5 over infinity, which is 0. Unfortunately, this makes the divergence test invalid. The limit is equal to 0, which means the series cannot be confirmed to diverge. So in this case, we have to say there's no information from this test. The third and final series produces a similar result. In the interest of time, I am not going to be doing that on the video. Instead, that will be on the posted notes. Okay, so a somewhat famous series is the sum of n equals 1 to infinity, and this is a good illustration on the limitations of the divergence test. If we take the limit as n approaches infinity of 1 over n, the answer is 0, which indicates we cannot say this diverges. However, the fact remains this series is divergent. So what that means is we need a different test to see whether this series converges or not. Because again, just the limit being not 0, well, there are series whose limit of sums or limit of terms is 0 and yet diverge. So we will now talk about a test that addresses the issues that come up in this series. So, one test that we can use is the integral test. If you remember from Calculus 2 or Calculus of Integrals, taking the area underneath the curve is an integral. We can also represent a sum as rectangles with a width of 1, given that each term can form a rectangle and its height times 1 gives the same value as what the sum would give. Moreover, if we do rectangles on one side, it will typically be greater than the curve, and on another side it will be less than the curve. So for example, for 1 over x, if we do left-hand rectangles, then the area of the rectangles, which represents the sum, is greater than the area under the curve. Well, now let's consider what happens if we take the integral from 1 to infinity of 1 over x. If we take the integral from 1 to infinity of 1 over x, we get natural log x. Natural log of infinity is infinity, which means the area under that function goes to infinity. Now, the rectangles have even more area than the function. Well, if the integral goes to infinity, that means the series must also go to infinity. And so, the sum from n equals 1 to infinity of 1 over n diverges to infinity. A similar thing can be done with 1 over x squared. We note that if we make right-hand rectangles, then the area of the rectangles for the series sum n equals 1 to infinity of 1 over n squared is less than the area under the function 1 over x squared. Taking an integral, we can then calculate how much area there is under 1 over x squared from 1 to infinity. Taking this integral gives us 0 minus a negative 1, as we note that x to the negative first is 1 over x. 1 over infinity is 0. Now, this area under the curve is not the same as the series. We note the gaps. However, that does mean this series should be expected to be less than that integral. So if that integral is a number, then that series should be also a number. So because that integral converges, the series with the same inside will also converge. And hence our two rules. If we can make a function such that the nth term is equal to the value of the function, if the integral converges, then the series converges. If the integral diverges, then the series diverges. And hence, by integrating the inside, we can figure out whether it converges or diverges. A key note, the integral does not give the value of the series. Okay, and please remember this last statement. By taking an integral, we are only determining whether or not the series converges. We are not determining what the value of the series is. By the way, in terms of calculating the value of an infinite series, aside from geometric series, it tends to be very difficult, and for this course, we will seldom calculate the value of an infinite series. It simply is beyond, and it is too much of a varied topic to cover in any reasonable length of time. So, we can use the integral test to determine whether a series converges or diverges. Now, there's a key caveat here, and that is the function has to be integrable readily. A lot of functions are either difficult to integrate or simply cannot be integrated analytically. So the integral test has significant limitations. However, for plenty of functions, it can be useful in determining convergence. So let's start out with the first one, the sum from n equals 1 to infinity of 7 over n cubed. To apply the integral test, we just take the integral of the nth term, replacing n with x, which actually is not entirely necessary because the variable in integration is a dummy variable. Once we take that integral, we simply see if the integral is equal to a number, or if it's equal to infinity, or if it just doesn't exist. If it's equal to a number, then the integral converges and the series converges. If it's equal to infinity, or if it doesn't exist, then the series is divergent. In the case of this first integral, the antiderivative of 7 over x cubed is negative 7 over 2x to the negative second. Then inserting the limits, infinity to the negative second is 1 over infinity squared, which is 0. Plugging in 1 gives negative 7 over 2. The result is an answer of 7 over 2. So the integral converges. Because the integral was the same as the nth term, that means the infinite series converges. And so the integral converges, meaning the series converges, and the sum from n equals 1 to infinity of 7 over n cubed converges. Now, let's take a look at the sum from n equals 1 to infinity of the square root of 2n minus 1. So to start out, we set up the integral from 1 to infinity of 1 over the square root 2x minus 1 dx, as that is an equivalent form for the nth term of the series being integrated. It can be shown using a u substitution that this integral becomes 2 times 1/2 times parentheses 2x minus 1 parentheses the 1/2 power. If we insert infinity into this, we end up with infinity to 1/2, or in other words, square root infinity. As it turns out, any infinity raised to any positive power will remain infinity. So, this integral goes to infinity and diverges. Since the integral diverges, it then follows that the series diverges as well. So, because the integral diverges, the series diverges, and we're able to move on. In order to save time, the other two examples will be shown only on the posted notes, not on the video. So, let's move on. From earlier, we saw that the series from n equals 1 to infinity of 1 over n was divergent, whereas the series from n equals 1 to infinity of 1 over n to the second was convergent. This is part of a structure known as p-series, which is any series that can be written in the form n equals 1 to infinity of 1 over n raised to the power of p. Notice how 1 over n squared is convergent, 1 over n is divergent. Well, and also notice that 1 is a unique power. For our first power, we have the number itself. Any power that is less than 1 has to be written as a root, that is, specifically any power between 0 and 1. Any number greater than 1 will have at least one integer exponent inside a root if it is so chosen to write it that way. So, this sum of 1 over n diverging is the breaking point of this. Any time that the power for n in the denominator is greater than 1, the series will converge. Anytime the power is less than or equal to 1, a p-series will diverge. So now, look below and see if you can identify which of these series converge and which of these series diverge. So, rewriting the first two, that is, the first series diverges because the cubed root of n squared can be written as n to the 2/3 power, that is less than 1, and so, by the rule of p-series, that is divergent. On the next one, rewriting the power results in n to the 5/4 in the denominator. That is greater than 1, so that is convergent. The next two also converge. The last one, it is worth noting that multiplying a series by a number will not change convergence or divergence. So multiplying the series n equals 1 to infinity of 1 over n to the 5th has no effect on the convergence, and 1 over n to the 5th forms a convergent p-series. P-series are nice, however, adding or subtracting numbers to the bottom immediately makes that single test not a valid form of proving convergence. It is possible to guess at convergence, which I would encourage you to pause the video and do here for these 4 series. However, guessing convergence from a pure math perspective is insufficient. It has not shown convergence. So we will need a stronger test. Now, again, it should be noted that these series are very similar to p-series, so we can be pretty sure as to what happens. We just need a formal way to be able to confirm our belief, so that it isn't just conjecture and rather it's a fact. The form of this comes in, one of the ways we can do this is comparing this series to a series we know converges. I'm going to take a look at the first and last ones on this, as these form very similar comparisons to p-series that are not that difficult to show convergence or divergence of. So for the first one, n squared plus 1 for integers greater than 1 is greater than or equal to 0. It's actually greater than or equal to 0 for any integers. However, for our purposes, we only need to consider integers greater than or equal to 1. Now, if we increase the denominator, that will decrease the value of a positive number. I mean, the classic example is if you have 5 cupcakes on a table and you divide it by 2 people, and you each get 2.5. If you divide it by 3 people, then you get less than 2.5. You end up getting about 1.6 cupcakes. So by increasing the value of the denominator, it decreases the value, and hence we have 1 over n squared plus 1 is less than or equal to 1 over n squared for all numbers greater than or equal to 1. Well, if we look at the sum of 1 over n squared, that is a convergent p-series. These two statements combined indicate that the sum from n equals 1 to infinity of 1 over n squared plus 1 converges. Now, let's take a look at the last one on this list, the sum from n equals 1 to infinity of the square root n minus 0.9. If we look at this, this is very similar to a p-series 1 over the square root of n, or in other words, 1 over n to the 1/2. Now, because we are considering integers that are 1 or greater, this is always greater than or equal to 0. Now, in this case, we are actually subtracting from the denominator. By the way, the denominator will always be greater than 0 because the lowest term in the series is n equals 1. Well, 1 minus 0.9 is 0.1. So again, this is positive. And moreover, because we are subtracting from the denominator and the denominator is positive, this means that subtraction will increase the value of the overall term. And so we can say that 1 over the square root of n minus 0.9 is greater than or equal to 1 over the square root of n. Now, the sum involving 1 over the square root of n is a divergent p-series. So if that's a divergent p-series, that means that sum goes to infinity. Well, if we have another sum that's greater than or equal to that, it should also go to infinity. And for that reason, we can show divergence of this series. So this gives us the 2 prime examples of series comparison. If we can show that every term of a series is less than or equal to a convergent series and all terms are positive, then the series converges. If we can show that every term of a series is greater than or equal to a divergent series and all terms are positive, then the series diverges. And this is the series convergence test. This is the series comparison test. So I would encourage you to read over this. I'm going to give a very quick summary. There's the formal version, which is good to look at. Again, in this case, the formal version has value on the problems. And then there is the math to English translation, as again, math definitions are not always written in the easiest way to understand. As a matter of fact, usually they're written in the easiest way to use, not the easiest way to think about. So for the first part, if we have a series where all terms are less than the terms of a series that converges and everything is greater than 0, then the series that is less than also converges. If we have a series, for the second case, if we have a series whose terms are always greater than a series that diverges, where all terms for both series are greater than 0, then the series with greater terms diverges. So this can be nice when integrals are not as easy to calculate. And we will see some examples below where integrating is at best challenging and at worst really problematic. So let's start out with the first series over on the left-hand column. The sum from n equals 1 to infinity of 1 over e to the n plus 3. Now note that 1 over e to the n can be written as 1 over 2.718. It does go on, however, the point being is the sum from n equals 1 to infinity of e to the n is a convergent geometric series. Now, similar to what we had discussed earlier, the denominator of our series in question, the sum from n equals 1 to infinity of 1 over e to the n plus 3, has a denominator that is larger than a convergent series. Because the denominator is larger, that makes the overall numbers small. Also note that because e to the n is always positive and we are only adding to it, the terms are always greater than or equal to 0. So given that we have shown that our series is positive and is less than or equal to a series that converges, our series must converge. And that's all we need to do for the series comparison test. Now, let's take a look at the series below it, the sum from n equals 1 to infinity of the cube root of n minus 0.5. This series is very similar to the series 1 over the cube root of n, which can also be written as 1 over n to the 1/3. This series is a divergent p-series. Moreover, the denominator for both of these series is positive. The lowest the denominator ever gets on the divergent p-series is 1. The lowest it ever gets on the original series, what we are trying to determine convergence for, is 0.5. So both of these denominators are positive, and the denominator for our series is less than the convergent series. So that means because the denominator is less, the overall series is more. So we can write that as an inequality. Now, again, the series sum from n equals 1 to infinity of 1 over the cube root of n is a divergent p-series with an exponent in the denominator of 1/3. Because our series in question is positive and greater than a divergent series, our series must diverge by the comparison test. In the interest of time, the final two problems on this slide will be not covered in the video, instead will be shown in the notes that will be posted. Okay, let's take a look at something that causes some issues with the comparison test. As unfortunately the series comparison test is not the only convergence test. Even if you include the integral test, there are more convergence tests. One of the issues arises when you do minor variations. The comparison just doesn't work. So let's take a look at the series n equals 1 to infinity 0.5 n to the fourth minus n plus 1. I want you to think to yourself whether this converges, as well as what issues there are with the tests we currently have. Hopefully you'll pause the video to take some time to think about this. So, first of all, this series is pretty similar to the sum from n equals 1 to infinity of 1 over n to the fourth. The series sum n equals 1 to infinity of 1 over n to the fourth is a convergent p-series. The temptation is to use a comparison with it. The issue is, if we plug 1 in for n, then we have 1 over 0.5, which is 2 for our series, and we have 1 over 1 for the p-series. So unfortunately, the comparison test does not work, because in this case, our series isn't always less than 1 over n to the fourth. The other temptation is, well, let's try integrating. The issue is, with integrating a denominator that's got 4 power minus the variable itself plus a number is an integral that is at best very difficult and at worst may very well not have an analytic solution. So unfortunately, the integral test doesn't work either. There is another option. If we take the limit of a series that converges over a series in question, and we can show that limit is equal to just a number, then we can show convergence. Hence, let's take the limit as n approaches infinity of 1 over n to the fourth over 1 over 0.5 n to the fourth minus n plus 1. If we take this limit, we can immediately use division by fractions to rewrite the limit as 0.5 n to the fourth minus n plus 1 over n to the fourth. Distributing the denominator and then inserting infinity gives a result of 0.5. The significance is, we saw earlier that multiplying a series by a constant does not affect convergence. And this says that eventually these series will only be off by a constant. And so from this limit, we can say that the series in question, 1 over 0.5 n to the fourth minus n plus 1, converges. This then forms the limit comparison test. So, if we have two series that have all positive terms, if we take the limit of the ratio of their terms, and the ratio is a number, it is not 0, then they both converge or diverge. If we take the ratio, we take the limit of the ratio where the convergent series terms are on the bottom, and it is equal to 0, which, by the way, this would mean that the convergent series has significantly larger terms than the unknown series, then the series converges. On the other hand, if we take the limit as n approaches infinity of the unknown series over a series that diverges and it's equal to infinity, that means the unknown series has terms that are much larger than a divergent series eventually. And so, if this is the case, then our unknown series diverges. So, the last thing that we will do as a part of this lesson, and I realize this is long, I appreciate your patience in getting through this, is we will apply this test to a couple series and use it to show convergence or divergence. So, let's start off with the first series shown on this page. The sum from n equals 1 to infinity of 1 over n to the third minus 1. The first step in applying a limit comparison test is to identify a series that is known to either converge or is known to diverge. If you think about it, a series that's similar to this first one that is known to converge or diverge is 1 over n to the third, and that is a convergent p-series. Now, we will take a limit of these two. Given that 1 over n to the third converges, we will put it on the bottom, as that way if the limit is a number, or if the limit is 0, it shows convergence. Calculating this limit, again, we can divide by fractions, and then, in this case, it ends up being valued, we would end up most likely dividing by the highest power of n and simplifying. Dividing by the highest power of n would give us 1 over 1 minus 1 over n to the third, plugging in infinity, ends up giving us an answer of 1. So we have shown that the limit as n approaches infinity of the terms of the unknown series over the terms of a series that converge equal 1. This means the series also converges by the limit comparison test. We now move on to the series below. In this case, again, it helps to compare this to a convergent p-series. So, comparing the series from n equals 1 to infinity of 1 over the square root of n plus 1, that can be compared with a p-series sum from n equals 1 to infinity of 1 over the square root of n. So, this is a divergent p-series, as the exponent on the bottom would be a 1/2 power. We can then set up a limit of the ratio of these. Because our comparison series diverges, we want to put it in the numerator or the top of the limit. By a similar process, this limit is equal to 1. That concludes this video. Do not worry about problems of the nature of these two, as again, this section is long enough, and in this course I will not be testing you on problems such as these final two series. If you would like to discuss them with me, you are more than welcome to come by my office and we can go over how to determine convergence of these. Thank you very much for your patience as you have watched this video. I hope you have a great break. If you watched this before Thanksgiving, have a great Thanksgiving. And otherwise, I will see you when you come back. Have a good one.